Right, so today what we're going to do, we're going to start talking about instruments. Um, all the We're going to start talking about all of this lot, and these instruments are driven by, some of them are driven by the vacuum system, some of them are driven by the electrical system. So we've talked about the electrical system. So we're going to start by talking about the vacuum system, and then I'm going to move on and talk about some of the other instruments, and then we'll talk about the pressure-based instruments. So we'll talk about the airspeed indicator, altimeter, and vertical speed indicator. So I don't know how much flying each of you have done, but we'll just have a quick go round. So Claire, what's this instrument here?
Sorry, I can't see it that well. It's got a bit of shine in
It has actually got a horrible shine on it, hasn't it?
it.
It's in the top left-hand corner.
I'm just trying to think.
It's always in the top left-hand corner of an aircraft, well, unless you've got an EFIS panel. It's
Is it speed? Is it
Sorry?
speed?
Yes, it's the where are we? There, it's the airspeed indicator. It shows you your speed through the air, and then as we come to the right, Rob, what's the next instrument?
Artificial horizon indicator.
Yeah, horizon. And then the next one along is the Will Hayes.
Is that the altimeter?
It's the altimeter. Then we've got a VOR, and then the bottom left-hand corner we've got will be.
Is that your turn coordinator?
Turn coordinator, well done. And then next to the turn coordinator, Claire, is the
Direction?
direction indicator. Ho, this is good. And next to that one, Rob.
Vertical speed indicator.
Yep. And then we've got another VOR here. And then in the middle, we've got a clock. And then here, we've got a suction gauge. So generally, these instruments, the airspeed indicator, artificial horizon, altimeter, turn coordinator, direction indicator, and vertical speed indicator, these 6 instruments are normally arranged like that on all aircraft. So the suction gauge, the clock, and the VORs can quite often be in a different place. And we're going to talk quite a lot in depth about each of those 6 instruments. So the first thing I want to do is talk about what powers them, because they all, some of them require energy, some of them are passive, and they just run off things they can measure directly. But there is a bit of a catch question, which you may come across in the exams, in that all instruments, no matter what the instruments are, have power going to them, some sort of power. Can anybody think what power would you need to run things like a thermometer or a clock or something like that? It's actually the lights that light the instrument up. So so be careful if that question comes up in the exam. There is actually every instrument does have some sort of power source, even if it's just the light to light it up at night. But principally, all of these instruments require something to run them, to feed them. Now, some instruments can run on electricity, on DC, electric. But the only trouble with instruments that run on DC electrics is that, of course, if these fan belt snaps, the alternator belt snaps, the alternator will stop spinning, which means everything's running off the batteries. We only get 20 minutes on the battery, which means that the instruments would all stop, So that means all the instruments must run on something else other than battery power. So what we do is we run them on compressed air. So the engine can run, as well as running an alternator and making electricity, the engine also runs a very small air compressor, and then there is, in the back of the cockpit, there is a whole load of pipes where compressed air is run into various systems and things, and that actually drive some of these instruments. And that way, even if the electrical system fails, or it's all fused and the circuit breakers have all popped, you've still got a little pump that's bolted to the engine that's making compressed air. So let's have a look at a typical diagram of this compressed air system. So basically what happens is that you've actually got a pump here that's actually just a very small air compressor. And what it does is that it's producing a suction that's sucking air through the instruments. And this is what we call a vacuum system, the vacuum pump. And it's just literally a small device. It's about 4 inches in diameter by about 3 inches high, and it's just bolted onto the back of the engine. So from the vacuum pump, it sucks air basically from the outside through an air filter, and then it sucks the air through various instruments, like this one showing you the artificial horizon and the heading indicator. This diagram that they've drawn here isn't quite correct, but it doesn't matter. And then it draws, and there's also a suction gauge in the cockpit that shows you how much air pressure there is. And then there's normally a warning light with some sort of switch in the circuit somewhere to show you if there's if the air pressure is too low or whatever. So why do we suck the air? Well, the reason we suck air and not blow the air through the instruments is for several reasons. If you take air from the engine and you put that into the cockpit, do you remember what the problem was? What the problem was when we talked about the heating system of taking any air from the engine and putting it in the cockpit?
Um, hold on a second. Oh, is it the harmful gases come from the exhaust?
That's it. Potentially, if there's a problem with the engine and we're producing carbon monoxide, you you don't want to be putting that air into the engine, into the cockpit. So we need to generate a couple of, maybe 2 or 3 pounds a square inch of compressed air. So instead of actually making having this pump air into the cockpit, what we do is we connect the tube, if you like. Instead of connected to the outlet, we connect it to the inlet, and then the little air compressor on the engine is sucking the air from the cockpit. So that way, if there's an issue with the engine, we don't pass that air into the cockpit. There's an interesting sort of thing to realize is that on the back of the instrument that's air driven, it just basically has an air in and an air out. And the instrument doesn't actually know if it's having air sucked out of it or air pushed into it. All it's interested in is knowing that there's a 2 pounds a square inch differential between the in and the in and the out. And the way these things work is that inside each side of each instrument, there's like a what there is there's the air has hits this disc, and this disc has got like little buckets in it, and the air hits these buckets and it causes this to spin. And this is where the instrument that needs some sort of energy to run it, it comes from this compressed air that's hitting this, going, and it causes it to spin round. And when I say spin round, I don't mean at like a couple of hundred RPM. I mean, this is spinning round at like sort of like 3,000 or 4,000 RPM. I mean, it's really going for it. Now there's two ways that you can get compressed air. One is from a small air compressor that's bolted to the engine, which we call the vacuum pump. Now there is another method of doing it, which is very popular on sort of more vintage aircraft. And they actually have a device called a Venturi. Now, there's a nice picture of a Venturi, so instead of me drawing one, I've actually got one here. Here we go. So if you actually take a tube and you pass air through it, so on this particular example, the air is going through this way, and you make the tube go thinner as you go in and then come thicker again, what happens is the air speeds up in the thinner section of the tube, and it creates a suction. The air pressure is lower as it speeds up, and of course that creates a suction here, and this suction drives the various instruments. And there's a nice little picture here. Here we go. This is actually what they look like. So they're bolted on the side of the plane. Is this like contraption called a Venturi tube, and there's an actual picture of it bolted to the side of like what looks like a tiger moth. But of course, you could probably see there could be a couple of problems with the Venturi tube, couldn't there? So, Rob, what do you think could be a problem with a Venturi tube system as opposed to a vacuum pump system for generating you a little bit of compressed air?
Because the Venturi tube's shaped similar to the theory of a carburetor, could you get icing inside it, which could impact your readings?
Well done. Yes, absolutely. Because of course, although you do get icing in it, and it's actually for quite a technical reason, actually, because of course the carburetor is because primarily gets icing because you've got fuel evaporating and you've got latent heat, and of course it has to take that heat from somewhere. But you are absolutely correct, Rob, because what happens as soon as you lower the air pressure, we were just talking to I was just talking to Claire a short while ago about what happens to the relative humidity, and of course that actually because moisture comes out the air, because we alter the relative humidity because we've lowered the pressure. If we actually cause moisture to come out the air has to cool, which can make the air, make the water that's coming out of it, that's condensing, will actually freeze. Yes, that's very, very good to have got that one. Will Hayes, can you think of another problem with a Venturi tube system on an aeroplane? I'll give you a clue. It's all to do with your pre-takeoff checks.
Pre takeoff, the plane won't be moving.
Absolutely. Well done. Yes. So before we take off, the plane's sat on the ground, isn't it? So there is no pressure, there is no air pressure coming from the Venturi tube, because the Venturi tube has to have quite a high airspeed. The plane has to be doing 30, 40 knots before the Venturi tube is going to start to create pressure. So that means that the first time you're going to know that you've got a problem with any of your instruments or your vacuum system is when you're in the air. Well, that's a fat lot of good, isn't it? And needless to say, of course, that you would seriously need your brains examining to sit in a tiger moth and take off into the IMC. And of course, sadly, people have done this in the past, discovered they've got problems with their instruments, and of course, haven't lived to tell the tale. So we've talked about the vacuum system. We've talked about some of the problems associated with running compressed air. So let's run through some of the instruments. I think we'll start with the easiest instrument of all, and that's temperature. Sorry, doggy, you're going to have to go. I need to forward. I don't care. You just have to. How do you move? There, doggies. So, how do we measure it? How do we measure temperature? Well, the easiest way to measure temperature is to obviously you can't use a traditional mercury thermometer in an aircraft. You know, you want to have an at a glance gauge, don't you? You don't want to start like trying to angle to catch a thermometer reading. So what happens is if we take two bits of metal and these are dissimilar metals, so typically you would have one would be copper and one would be steel, and you connect them together at the end. They will have different rates of expansion. So what will happen is as it expands or cools, this bit of metal will bend upwards or it will bend downwards. It's called this is called a bimetallic strip. Now this can be quite a good way of powering an instrument, because what we could do is if I took this bimetallic strip and I made it into a little coiled spring, so it looked a bit like this. So I had so now we've got the same thing but made into a nice little coiled spring, and then I put like a needle here. Then what would happen is, as this bimetallic strip expanded and contracted at different rates, then it would cause this to rotate round or in one direction or another, and then this needle would move left or right. So whose turn is it next? Will Hayes, I think. Will H. So Will, where in a plane do you find this?
Isn't it? Is it in the middle of the instrument board?
No.
Oh no! Is it to the right?
Yes, it's to the right, and it's right up out the way in a place you can never see, and it's right up here. It's just over here, and why is that? But you're right, it would be more convenient to stick it in the dashboard, wouldn't it? But it's not. It's stuck right up over right on the extreme edge of the plane, because it's the OAT, in other words, the outside air temperature gauge. And of course, because it measures the outside air temperature, it has to be on the side of the plane, so the little probe that goes into the instrument actually sticks out physically outside of the plane. So that means from the cockpit, you can look up over your right-hand side and it shows you what the outside air temperature is. So that's how the first instrument works. The simplest one, the outside air temperature gauge. So Claire, does the outside air temperature gauge have a connection, an electrical connection?
I'm going to say no.
Let's catch question.
Is it no?
No's the obvious answer, and it's a catch question. So the answer is obviously yes. Why has it got a wire going to the outside air temperature gauge? What do you reckon?
To light it up at night?
Yes, so it's got a bulb in it that lights it up. So since we've got some of these instruments will work quite happily without electricity, they're only electricity sources to light them up. What do you think might be a useful thing for us to take with us in an aircraft if we're going to fly at night?
A torch?
Torch, yes. And in fact, you'll find that it is part of the minimum equipment list in a plane is that pilot must carry a torch, just purely so that you can just, if you want to find out what the outside air temperature is and you've lost all your electrics, you can just like shine a torch over and it will show you what the outside air temperature is. Now, there are other sorts of temperature gauges. They don't all work on the sort of 1940s kind of bimetallic strips. There are resistive sensors, electronic ones, and most planes nowadays, like most cars, on the cockpit, there is just a tiny little thing that says, 23 degrees or whatever. Just like you get in any modern car. Now, how are we going to convert? Sometimes we have to convert centigrade to Fahrenheit. So how are we going to do that? So can you have a look at your whiz wheel? Grab your little computer. And if you have a look on your computer, right on the bottom, can you see there's a scale that says centigrade and Fahrenheit? And if you have a look, you can convert from one to another. So if you have a look on your whiz wheel, for example, and you have a look at 0 degrees centigrade, what is 0 degrees centigrade in Fahrenheit? Will be?
What was it? 32?
Yeah, about that. And you'll see if you look, Will H, if you look at 0 degrees Fahrenheit, what's that in centigrade?
-16. -16.
Not really. 0 degrees Fahrenheit in centigrade is not -16, it's minus. You've got a little dash there, haven't you? The dash is at minus 15.
Minus 18.
Yeah, it's about minus 18 degrees centigrade. Now, in the exam, you're allowed to have you'll have this with you in the exam. Now, so you might be asked questions on the ISA in the exam, but the question will never be in this form. So, for example, they might say, which of the following represents the ISA? And they'll have a list of 4 different answers. And they might have like 21 degrees centigrade. Now, chances are they won't say 15 degrees centigrade. They'll probably say something like, instead of 15 degrees centigrade, they'll say something like 59.5 degrees Fahrenheit or something like that. And of course, you can work out if that's the right answer by just looking on your little whiz wheel, and then you find the 15 degrees. Find 15 degrees centigrade, and then you'll see that roughly lines up with about 59 degrees Fahrenheit. And the secret with all of those numerical questions in the exam is you've got to RTFQ all the time. So whenever you see a question that's giving you a set of numbers, RTFQ, and just to see if you're looking at C's or feet or meters or millibars or whatever. Whatever the question is stating, just read it very, very carefully. Because chances are there'll always be one answer where they just work on the assumption that if somebody hasn't read the question, it will lead you up the wrong path. Now, on the outside of the plane, there are some pressure sensors that's sensing the outside air pressure. Sadly, the engineers that designed the 737 MAX didn't attend any of our AGK lectures, but had they have done, then they would have fully understood all the implications of all these various sensors and things and bits and pieces. Now, what these sensors actually are is they are measuring the various air flows around the aircraft. Now, we're fairly fortunate in that with the planes that we fly, we don't have to convert these into an electronic form. So we don't have the sort of Boeing issues, but we use those pressures directly. So what sort of pressures what sort of sensors are we looking at? Well, there's 2 I'm going to be covering today. In principles of flight, we'll be talking about angle of attack sensors, but the 2 I want to talk about today is static pressure and dynamic pressure. So what static pressure is, that is just simply the pressure of the air outside the aircraft. Now, the pressure outside the aircraft changes, obviously on a day-to-day basis, because the air in the atmosphere where changes for each day, and of course it changes as you move from one place to another place to another place. The sort of atmospheric conditions make the air pressure different. But what's the primary thing in a light aircraft that, or in any aircraft, that affects the pressure that's outside the aeroplane? Claire?
It's speed.
That's a good answer. That's not the answer. Yeah, I didn't answer the right. You are correct. I didn't really ask the question very well, did I? But what I'm after is the general air pressure that's around the aeroplane. What is the number one thing that's affecting the pressure that's around the aeroplane?
Temperature.
Height. So as you go up, as you ascend in the air, the pressure reduces, doesn't it? By how much does it reduce, Claire?
1 millibar per 30 foot.
And what does it start off at in ISA?
1013.
Well done. So the pressure reduces by 1 millibar every 30 foot, and it starts off at sea level 1013. So in actual fact that the pressure as you go up into the atmosphere changes an awful lot very, very quickly, doesn't it? Whereas you find that the difference between a high pressure day and a low pressure day might only be sort of like 50 millibars or something like that. But you see, this is changing by 1 millibar every 30 foot. So that means that you don't need to go that high to have quite a dramatic change in air pressure. So we've got to measure this outside air pressure. But Claire was was kind of on the right rails. Is that how the shit do you measure the pressure that's outside of something when it's moving along? Because anything that's moving through the air is going to create sort of lift force, which is going to create obviously reduced pressure to create lift. We've got dynamic pressure because we're pushing something through the air, so there's some sort of air resistance that's going to cause the pressure to increase. So you can probably imagine in an aircraft, there's like the air pressure outside is going to be different all over the damn outside of a plane, and we've got to find a way of measuring the outside pressure because we want to know what it is. Because if we know what the outside pressure is, we can probably work out how high we are. Well, there is actually when you design a plane, there is actually a spot, and you tend to find that on the side of the plane, just before the wing is, you tend to find that the plane has a sort of shape, like, you know, if you look at the plan view of a typical light aircraft, it's sort of like the engine cowling comes back here, and then you've got like the wings that sort of stick out here, and then you've got like the sort of cockpit is here, and then you've got like the propeller is here. This is the plan view, and there's a point about here, and this isn't just true of light aircraft, it's also true of passenger jets and everything, but where if you're moving through the air, that the pressure here represents the outside sort of ambient pressure extremely well and accurately. Obviously, you can't measure the pressure here because you're going to get the ram air effect and the propeller airflow and things. You can't measure the pressure here because, of course, you've got lift force and reduced pressures from lift, and of course you can't measure it beyond the wings because you've got some sort of turbulence produced by the wings and things and bits and pieces. So you've got smooth air in this point here, and this represents a very good place to sample the air. So what you tend to find is that on planes you've got a tiny little thing here called the static vent, and it's sat on the side of the plane. And what it is it's got a tiny weeny little hole in it. And when I say tiny weeny hole, I mean I'm only talking about a hole that's 2 or 3 millimeters big. And then from here, there's a small plastic tube. It's only about a 1/4 inch diameter. There's a plastic tube that goes into the actual cockpit. And this is the this is called the static vent or the static port. Now, of course, that if the plane is flying sideways slightly or in one way, you can probably imagine if it was like flying this way, just tilting, flying sideways a little bit, then this would show an artificially higher outside air pressure. So you do tend to find that some planes what they do is they've got one on each side, and they have a tube connected to each side with a little T-piece here. That simply connects the tubes together. The idea being that if the plane is just flying slightly sideways, one of them would be having a slight suction and the other one was receiving slightly extra pressure, and the two would balance one another out. So you might well find that the static port is on. You've got the matching one on each side of the plane, and the static port is measuring the outside air pressure. Sorry, that's bollocks. The static port doesn't measure anything. The static port is representing the outside air pressure. So that's the static system. And I'll talk about the pitot system now, is that besides just measuring what the outside air pressure is, we want to also know what the ram air is. In other words, how much wind the plane can actually see, how much force there is on the plane. Now, obviously, how much force there is on the plane is a direct function of how fast we're going through the air. So what there is on the bottom of one of the wings, you'll find there's a device. It looks like this. It sticks down from the wing. And has a little hole in it here. And what happens is the air, as the plane is going through the air in this direction, the air comes in here and it pressurizes inside this tube. And at the top of this, where it's bolted to the underneath of the wing, there is a tube here, another plastic tube. It heads off to your cockpit. A little plastic tube. And obviously the pressure inside here goes up the faster you go. Now, there's a couple of other little bits here. There's a drain hole here in case there's it gets water in it, so the water can actually drain out of it. And because it's getting ram air into it, these things can ice up very easily inside them. So you tend to find that what happens is that inside this metal, there's a coil of wire. And this is connected to Earth. And this is a wire that's a heater wire. And this is connected to the pitot heater. And in the cockpit, there's a switch where you can click the switch, and there's a pitot heater, and it will heat up the pitot tube. It's not quite on my diagram. I can't show it to you because it's just slightly underneath the steering wheel. And when I say it heats up the pitot tube, I don't mean it gets it like mildly lukewarm. I mean, when it heats up this pitot tube, it's very hot. I mean, like, for example, if you, in your pre-flight checks, turn on the pitot heater and you have to go out and check to make sure the pitot heater system is working. And whilst you're heading out to check the pitot heat's working, you obviously you take a mobile phone call, you have a chat with your mate, you do a few other things, and it takes you like 2 or 3 minutes to get from the cockpit door to the pitot heater. And then you put your hand on the pitot heater tube, on the pitot tube to see if it's hot. You'll burn your hand. I mean, it will be 100 degrees centigrade. It gets very, very hot. And it consumes a lot of electricity, these pitot heaters. So generally, as part of your pre-flight checks, you'll probably find that although it's in your pilot's operating handbook that you should check the pitot heating system before flight, which you always do in the UK, quite often in Cyprus, you'll find that your instructor will tell you that on a good day, when there's no risk of any form of icing ever, on your pitot tube, he'll probably say, don't ever bother to check your pitot heater because it consumes so much electricity, we don't want to risk flattening the battery. or sometimes he'll ask you to check the pitot heater system, maybe not quite as per the pilot's operating handbook. I mean, certainly sort of more experienced pilots, you tend to find that what you do is you sort of like, if you want to check the pitot heater, you sort of turn the pitot heater on, you leap out the plane, quickly check to make sure it's getting warm, and leap back into the plane and turn it straight off. You don't sort of include it in your walk round drill that also includes doing some fuel strainers, checking the propeller, checking the brakes and all that sort of gear, because by the time you've done a walk round check of the rest of the plane, this has probably flattered your battery. So these two pressure sensors then are the static pressure and the pitot pressure. So into the cockpit behind the instrument, you've got two plastic tubes. One is connected to your static ports. The other one's connected to your pitot tube that's measuring this ram air. So I'm just going to run that. I've got a nice quick video of that, and then that'll probably be time to have a quick break.
Paul, just whilst you run that video, is that pitot pressure then, just for me, is that dynamic pressure, whereas
Yes,
your static then is static pressure?
No,
Yeah.
it's what they call it is. Well, since you've mentioned it, let's just cover it.
Sorry, everyone.
No, that's fine. So this pitot tube the plane is obviously moving in this direction. That means that the air is moving here. So this is actually the pressure this is seeing is the pitot pressure. But if you think about it, what actually is the pitot pressure made of? Well, it's actually two bits, isn't it? Because it's also measuring the static pressure, isn't it? So in actual fact, what you've got coming out of here in this tube here is you've actually got you've got static pressure plus dynamic pressure which is giving you your pitot pressure. Can you see that in the
Yeah, I got it. Yeah.
Because this if the plane wasn't moving, if the plane was stationary, what would this tube be? What would this tube be what would be in this tube?
Just static pressure.
It would be static pressure. Yeah. So now be very careful if this question comes up in the exam, because you can imagine what people think is they say, well, hang about, the plane's not moving. The pressure in this tube's going to be zero. And no. If the plane's not moving, this tube is just showing static pressure. In other words, the pressure in this tube is going to be the same as the pressure that's in the tube that's connected to the two static ports, isn't it?
Yeah.
Yeah, because this is really, if the plane's not moving, this is a static port, isn't it? It's a hole connected to a tube connected to the outside of the plane. Only when the plane's moving does this pressure increase, and of course it is static plus dynamic, and so what's coming out this tube isn't necessarily dynamic pressure; it's static pressure plus dynamic pressure, which we call the pitot pressure. We're going to talk a little bit more about that when we cover the airspeed indicator, which we're going to do after our break. That's a good point to bring up. So let's just so I'm looking for the pitot static instruments. Here we go. Right, this is a little video.
Static system. The pitot-static system is connected to the airplane's altimeter, airspeed indicator, and the vertical speed indicator. These instruments tell the pilot how high they are, how fast they are going, and how fast they climb or descend. These are determined by measuring the pressure of the atmosphere. Before we go any further, let us become familiar with the atmosphere. If we take a column of air, starting at the ground, and traveling up all the way into space, you notice that the molecules of air at the Earth's surface are much more compacted together than the molecules up in space. The reason for this is gravity. Since air is matter, it has weight. So, all the air molecules at the top of the column are pushing down on the molecules below them, which compresses them. This compression results in a higher pressure at sea level compared to the pressure on top of a mountain. How much of a pressure change are we talking about? Well, if we say the atmosphere goes up to about 375 miles above the surface of the Earth, 50% of those air molecules would be found in the first 18,000 feet of the surface. So, because the pressure of the atmosphere decreases the higher up we go, our pitot-static instruments are able to measure that pressure and calculate our altitude and speed. The pitot-static system gathers its pressure information from two sources, the pitot tube and the static ports, hence the name pitot-static. The pitot tube is designed to measure the pressure of the air as the airplane flies through it. In most smaller aircraft, this tube is located under the wing so it can measure the flow of air without any interference. Sometimes aircraft manufacturers will use a pitot mast instead of a tube shape, but it still functions exactly the same way. On the backside of the tube, there is a drain hole, which allows any rain or water that is collected while flying to drain out and not go into the system. Finally, the pitot tube can also be heated. This is used to prevent ice from forming on the tube, which could potentially block the hole and prevent the system from functioning correctly. The counterpart of the pitot tube is the static port. The location of this port will vary with different aircraft designs, but should be in a location where it can measure the static pressure of the air, unaffected by the dynamic airflow around the airplane. On the Cessna 172, the static port is located on the left side of the forward fuselage. The pitot tube and static port openings are connected to tubes that join into the pitot-static instruments. The pressure inside the instruments match the pressure of the outside atmosphere. All three pitot-static instruments connect to the static port, but only the airspeed indicator connects to the pitot tube. Sounds simple, right? Let's discuss how each pitot-static instrument works. Altimeter. Perhaps the most basic of all pitot-static instruments is the altimeter, which displays the airplane's altitude. The instrument contains a set of aneroid wafers which expand and contract based on the pressure. The air inside the wafers is trapped, but the air in the rest of the case is able to change to match the pressure from the static port. As we increase altitude, the static pressure goes down. This means that the air inside the case will escape out the back and result in there being less air pressure in the case compared to the wafers. Because of this, the wafers will expand until both pressures are equal. Getting the wafers to result in an altitude readout is done through the series of gears, pinions, arms, and levers, also known as the mechanical linkages. These linkages will rotate the hands on the face of the instrument and show the airplane's altitude. Now, when the airplane descends, the opposite happens. Descending to a lower altitude results in higher static pressure. Air from the static port will now enter the case of the instrument and squeeze the aneroid wafers until both of the case pressure and the wafer pressures are equalized. Mechanical linkages will then rotate the hands on the face to show a lower altitude. The face of the altimeter contains three hands, the 10,000 foot, 1,000 foot, and 100 foot hands. These hands move clockwise and counterclockwise to display the appropriate altitude. Most altimeters in smaller aircraft will only work up to around 20,000 feet, but those airplanes usually can't get that high anyway. Here's some examples of altitudes. 3,000 feet, 8,400 feet, 12,000 feet, 5,280 feet. This altimeter is actually called a sensitive altimeter, not because you have to hug it every once in a while, but because it can be adjusted for the current atmospheric pressure. Because the pressure at any given point on the Earth never stays the same, altimeters would always read incorrectly. Fortunately, pilots can correct this issue. Once the pilot knows the current atmospheric pressure, also known as the altimeter setting, all they have to do is rotate the dial on the lower left side of the instrument until the current pressure is selected in a little window on the face, called the Kollsman window. This then realigns the gears inside and the instrument reads accurately. The realignment is accomplished by rotating the entire inside mechanics of the instrument. Vertical speed indicator. Another instrument that uses only the information from the static port is the vertical speed indicator, more commonly called the VSI. The VSI measures the vertical speed of the aircraft in terms of feet per minute. This is accomplished by comparing the current pressure of the air with the pressure of the air from a few seconds ago. Inside the VSI is a diaphragm connected to some mechanical linkages that move the needles on the face of the instrument. The diaphragm has a direct connection to the static port, meaning that the pressure inside of it matches the current atmospheric pressure from the outside. The case of the instrument is also filled with static pressure, but the connection between the case and the static port is constricted by what is called a calibrated leak. This calibrated leak is nothing more than a tiny hole, which limits the rate at which the pressure of the case can change. When a plane climbs or descends, the diaphragm pressure will change instantly, but the case pressure changes slowly. This results in two different pressures. The difference in pressure allows the instrument to display the vertical speed. Be aware, however, that it takes a few seconds to read accurately, so anticipate a slight amount of lag. Here's an example of how it works. Say you have a Cessna flying at 3,000 feet. The air pressure and the diaphragm in the case are the same, so the VSI is reading 0 feet per minute. If the Cessna starts to climb, the air pressure in the diaphragm is decreasing, but the case pressure is decreasing more slowly. This results in the case having a higher air pressure than in the diaphragm. This higher air pressure will squeeze the diaphragm and make the VSI read a climb. Once the aircraft levels off again, the case pressure will finally equalize with the diaphragm, and then the VSI will show 0 again. Airspeed indicator. The airspeed indicator is the only pitot-static instrument that uses both input from the static port and the pitot tube. The pitot tube is used to measure what's called ram pressure. The faster the airplane travels, the greater the ram pressure is. The ram air entering the pitot tube gets sent to the airspeed indicator and, similar to before, goes into a diaphragm. The greater the pressure, the more the diaphragm expands, so the diaphragm will expand as the airspeed increases. Then, through mechanical linkages, the appropriate airspeed will display on the front of the instrument. But what about the static port, you ask? Well, remember how the pressure of the atmosphere changes with altitude? Well, if this wasn't taken into account, then the airspeed would indicate different speeds at different altitudes, even if the plane was actually going the same speed. To fix this, the static port connects and fills the case surrounding the diaphragm with static air. This will subtract out the static air pressure that the pitot tube captured and only allow for the dynamic pressure to be read on the instrument. This keeps the airspeed indicator reading the correct values no matter what the altitude of the airplane is. The face of the instrument displays color-coded speed ranges that the pilot should be aware of while they fly, to avoid exceeding any limitations of the aircraft. The green arc is for normal operations. The white arc is when you're allowed to extend the flaps. The yellow arc is limited to flight in smooth air only. The red line indicates the maximum allowed speed.
inside the airspeed indicator, this is the case that's behind the airspeed indicator. So the static pressure comes into the case of the instrument. So inside the case, this is sitting at the outside pressure on the aircraft. And then the pitot tube comes along from another plastic pipe, and it's connected to this capsule in the this very thin metallic capsule inside the instrument. So what happens is that you can probably see that the difference between the static and the pitot pressure is causing this capsule to expand and contract. Now, if the static pressure and the pitot pressure are the same, then this capsule won't be actually expanding or contracting, because it's just looking at the difference between this pressure and this pressure inside it. So as we increase the pitot pressure, this capsule is going to get slightly bigger and expand in and out a tiny weeny bit. Then as it expands in and out, it's connected to a sort of like an arm that's got tiny weeny teeth on it. And then that teeth is in turn connected to a small cog. And then that cog is then connected to a larger cog that's driving another. So everything is geared so that a tiny weeny bit of movement here creates quite a big movement of this needle here. So this bit's only moving by, half a millimeter, but this is actually causing the needle to move all the way round from one end of the dial to the other side of the dial. But the significant thing, you can probably see that we've done quite a clever trick here in that what we actually have inside the case is this here is the static pressure, and because here we've got the pitot pressure, which is static and dynamic, essentially what we're doing is we're just cleverly reading the dynamic pressure. So in other words, we've subtracted the static pressure off the actual pitot pressure by putting the static pressure here on the outside. So all we're doing is monitoring dynamic pressure with this capsule that's expanding and contracting. So the faster we go, basically, the more the pitot pressure, or should I say, the more the differential between the dynamic pressure and the static pressure, the more this capsule will expand and the more the needle will read. So what does it actually read? Well, let's go through. Let's actually look at a typical altimeter and what's marked on a typical altimeter, shall we? So we've got, hopefully, that the altimeter we've got in the plane is a slightly better version than that one. There we go. That's probably a bit better. So this is the needle I was talking about. So the needle of the airspeed indicator will naturally go round the instrument as we get faster, as the airflow goes over the instrument. And it's divided into a series of arcs, and the instrument will probably, let's just draw some of these arcs in. These arcs are color coded. So the first arc is a green arc. So this is shown on your instrument in green. And this is the normal operation arc, and it will I'm just exaggerating a little bit because otherwise I'll run out of, you won't be able to see it clearly. So that's your green arc, and it will typically start at about, I don't know, let's say in a Cessna it will probably start at say 50, and it will go up, and it will probably be sort of like, I don't know, sort of like 60 here, 70, 80, 90, probably maybe 100 or something here. And this is the normal operation arc, and showing you what your airspeed is. Now there's another arc just inside that, which is whoops, won't be that big, will it? Let's draw as a small one. So this is the white arc. This is green, this is white. Of course, the back of the instrument is black, so this white arc is obviously makes a lot more sense than me trying to draw a white arc on a white board. Now, all of these airspeeds have got different names, so I'm going to cover all of these names, and you will need to know these for the exam. So this white arc is your flap operating arc, and this speed here, this first speed here, is called VS0. That's the minimum speed the aircraft can fly with flaps. So what happens will be if you try to fly the plane slower than the minimum speed?
Surely you'll lose altitude.
You'll stall.
Oh, okay.
You'll stall, and yes, you'll definitely lose altitude. How quick you lose altitude is a function of how much you stall by, and what type of aircraft you're flying. Some planes, if you stall them, you'll definitely be requiring a change of underwear when you land, assuming you survived. But this is VS0, the minimum speed you can fly with flaps. And this speed here, the top of the white arc, is called VFE. your flap extending speed, your maximum speed you can fly with flaps. Or sometimes called the flap extending speed. Yeah, that's why it's called VFE. It stands for flap extending. In other words, if you were slowing down and wanted to put your flap, the reason it's called flap extending is because typically you would be slowing down, approaching an airfield, slowing down. I want to put my flaps out. I want to extend my flaps. I can't yet. Here we go. Right, as soon as I reach VFE, I can put the flaps out. So this speed here, this is your normal operation, and then from normal operation, we then have another piece here. So this is coloured yellow. So this is your cautionary speed. And then you've got a red line at the end of it. And this is your BNE, your never exceed speed. And then you've got another speed that's sometimes marked, but it's a function of the air pressure and all sorts of other things. There's a speed typically here. And this is VA. Which is your, this is the maximum speed that you can go in turbulence. And it's normally a function of how strong the rudder is on an aircraft. So that's basically your speed. So this one here, this speed here, the end of the green arc is called VS1. So this is the minimum speed without flaps. You'll notice that the plane can fly slower with flaps than it can without flaps. Well, that's kind of expected, isn't it, really? Because that's the purpose of the flaps, is to make it so you can fly slower for takeoff and landing. So VS0 is bound to be a bit less than VS1. And if ever you can't remember which way around these two go, just remember that as the needle goes up, it gets to 0 before it gets to 1. Well, that's kind of logical, isn't it? And of course, the plane can fly slower with flaps. So this white arc is going to be there, not here. And obviously that's going to then be the 0 because you get to 0 before you get to 1. So got a nice little picture of it. So here we go. So we got here we go. VS0, VS1, VFE that we've talked about, which is the end of the white arc. VA, your design maneuvering speed. VNO is your end of the. I got this wrong, but never mind. VNO is your. The VNO is the arc, and the VA is your turbulent print. Let's get rid of this slide because it's crap. It's not right. That will just confuse everyone. Right. So unfortunately, in this PowerPoint presentation, there's a lot of things that aren't quite right. Let me just have a quick look in your books to make sure that your book is actually correct. 291. Yeah, if you have a look if you bring up your books, yeah, can you see you've got on chapter 25, pressure instruments. Yes, you see it's got here the, yeah, your book is in fact, yeah, your book's correct in that VNO is shown at the end of the green arc, which is what it should be. So your books are actually correct. Now, how am I doing for time? I'm doing good. So now I need to mention this briefly in that we will be covering this a lot more in depth though when we talk about principles of flight. The airspeed indicator is actually showing you what the wings are also seeing. Now, I know that might sound a bit of a stupid thing to say, but what I mean by that is that imagine you climb higher and higher and higher. Well, what's happening is the amount of molecules that's in the air per cubic meter is less. And that's what we mean by you've got less pressure. So that means if you've got less molecules of air that the plane's flying through, then you'd expect the wings to not produce as much lift. But in actual fact, the propeller and all the other things in the plane actually accommodate this, and the plane actually gets faster. So in other words, the amount of molecules per second that's hitting the wings actually remains the same as we climb. So you tend to find that if you're flying along at say sort of like 90 knots and you start climbing and then you level off at sort of 5,000 feet, you'll still be doing 90 knots. In other words, the airspeed indicator will be showing 90 knots, and what the wings are seeing is still 90 knots. In other words, the molecules of air per second that's hitting the wings will still be the same as it would be on the ground. But because there's less molecules up higher, that means the plane is actually flying faster over the ground. So that means that 90 knots at sea level is slower than 90 knots at 5,000 feet, which is slower over the ground than 90 knots at 10,000 feet. So this is why all aircraft fly at height. I mean, you ever wondered why a passenger jet flies at like 30,000 feet? Yeah, it's got to spend all that time getting up to 30,000 feet, flying around at 30,000 feet, then descending all the way down from 30,000 feet. Why the hell does it climb to 30,000 feet? I mean, you know, it could fly around at 10,000 feet and not have to bother about climbing all the way up to 30,000 feet, surely. It doesn't just climb to 30,000 feet just because there's less planes up in the air and it's got a lesser chance of hitting them. It climbs to 30,000 feet because of these these molecules of air thing. In that, if the plane is doing if the plane is flying at 500 miles an hour, or was capable of flying at 500 miles an hour at sea level, and it climbed to 30,000 feet, and it still flew at 500 miles an hour, using the same amount of fuel, using the same thrust, using the same everything. In actual fact, over the ground, if we looked at its GPS readout, it would be doing substantially more than 500 miles an hour. It'd probably be doing more like 600 miles an hour. So in other words, you've got 100 mile an hour worth of increase in speed over the ground for nothing. But of course, the airspeed indicator is still going to show like 500 miles an hour, even though in reality, your speed over the ground is 600 miles an hour. Now, we call this, what I'm looking at here, IAS, indicated airspeed. Now, IAS is what is shown on the airspeed indicator. Our speed over the ground is called TAS. Oops, I'll call it that. So TAS is true airspeed. And GS is our speed over the ground. So TAS is the difference between our indicated airspeed and our true airspeed, because we're just flying higher, and the ground speed is TAS, but obviously we might be battling a headwind or we might have a tailwind, which means not only is our TAS different from our IAS, but our GS is going to be less or more, just purely because there will be wind blowing the aircraft along, or we're battling a headwind. In other words, the air that we're flying in is also moving over the Earth's surface, giving us IAS, TAS, and GS. Now, I'm not going to cover it, but I just pointed out to you that if you can grab your whiz wheels, can you have a look on the outside of your whiz wheel, and you will find that there is something here. You'll find that there's a thing called true airspeed and rectified airspeed, and inside your whiz wheel there's a window here, and basically what you can do is you can actually compensate and calculate what effect that the outside air temperature and the altitude you're at is going to have on your airspeed, and you can actually calculate on your whiz wheel the difference between IAS and TAS. In other words, if you set your temperature and your height you're at, you can convert from IAS to TAS. and there is a way of doing it on your whiz wheel. And then, of course, when we study navigation, we'll go into this in a lot more detail, and we'll also then be talking a lot more about ground speed. Now, let's have a think about some of the things that can go wrong. Because the things that can go wrong are the classic exam questions. In other words, the exam question will be worded something along the lines of something's happened to your plane. Would you expect to happen to the various instruments? So the airspeed indicator is a classic one of what kind of things can go wrong with the airspeed indicator. Let's think first about the pitot tube. And the pitot tube has got an insect stuck in it, and it's blocked, completely blocked solid. So if the pitot tube was blocked solid, and I got in the plane, so the static port is working great, right? And that's reading accurately, but the pitot tube is completely blocked. So, Rob, when I got in the plane, what would my airspeed indicator show me?
You get no dynamic, so you just have static pressure only in the case.
Yes, although the pitot tube, would still have in it the static pressure from like before, wouldn't it?
Yeah, so it would have whatever pressure was in there before it got blocked, I guess.
That's right. That's exactly right. So what would actually the needle be showing you?
The pressure it was at the time, so it would be a false reading.
It would, but typically what would happen is that let's say that instead of it being completely blocked, more likely it's got stuck by an insect in it. So chances are that the pitot pressure would actually be equal to the static pressure. In other words, it would take like 5 or 10 minutes, but the pressures would actually eventually equalize. So when you got in the plane on the ground, it would show, the needle would show 0.
Okay. Yep.
Right. So you taxi out to the hold point, and it's reading 0. And that's what you'd expect it to read, isn't it? So everything's going fine up till now. So by Bravo Charlie, India Yankee, clear takeoff. Clear takeoff, India Yankee, full power, off you go down the runway. You're starting to build up speed, getting faster and faster and faster. What will your airspeed indicator show now?
If it's
0.
Sorry, yeah.
It's
Well,
still going to show you 0, isn't it?
yeah, because it's not getting any of the dynamic pressure through.
No, because that's okay. Will H, what are you going to do about it? Quick.
Well, you can't take off. Emergency land.
Well, you're already on the ground. You're running along.
Vacate the runway then.
Well, you just abort the takeoff, don't you? So, in other words, you just bring the throttle back, bring the plane to a nice halt on the runway. Tell air traffic control that you've aborted, and you're vacating by the next taxiway. Yeah, taxi back to the flying club. Investigate why your airspeed indicator's not working. And of course, the reason the airspeed's not indicating is because it's either blocked or it's iced up or something. So that's a blocked thing on the ground. And in fact, part of your checks, as you apply power on the runway and you get faster and faster and faster down the runway, one of your first calls you do as a pilot is you look at your airspeed indicator and you shout airspeed live. And what you mean by that is airspeed live means the needle's moving. That's all you're interested in. Airspeed live means your airspeed indicator is making a reading of some sort. So that's a typical test of a good pilot, and your instructor will expect you to do that as you apply power and you start gathering speed down the runway. After about 5 or 10 seconds, he'll expect you to look at the airspeed indicator and just say airspeed live. And if it's not live, bring the power back, bring the plane to a nice slow down, come off at the next intersection. It's not an emergency. It's just oh shit, something's not working. Come off at the next intersection. I'm going to think about it. Claire, why would you not want to go airborne with the with an airspeed indicator not working? What would be the really dangerous thing?
You wouldn't know when to put the flaps up and down.
And you wouldn't know when the plane was going to stall or whatever, would you? You would not be able to fly the plane properly if you did not know how fast it was going. Yes, sir. That's correct. So airspeed live is always a check. Right. So now let's think about something a bit more weird, in that now you have to get your head around these things, is that the airspeed indicator is measuring the pressure difference between the static port and the pitot, isn't it? So as the pressure difference between them gets more, so that the airspeed's going to increase. So that now the dynamic pressure is always going to be much greater than the static pressure, because that's what airspeed is. So let's say we're flying along and everything's working fine, so we've got a nice airspeed. And who's next on my list? Will. Sorry, Will, you've got the horrid question now. So Will B, you're flying along, everything's fine. And your static port gets blocked. Tell me, what's your airspeed indicator going to read? Your static port has got blocked. What do you reckon? What do you reckon, Will? Any idea?
Would it just cause it to freeze at the value that it stopped at? Whenever
Absolutely, you're dead right. Because the static pressure that it's blocked at is still the right static pressure anyway, isn't it? So it'll just carry on showing the correct airspeed. And of course, there's always an exam answer that says it will show 0. No, it won't show 0. It will only show 0 if the pitot tube gets blocked. So you are correct. It will actually carry on reading the correct airspeed. Now, what's going to happen if I start descending? What do you reckon, Rob? Rob, if I start descending,
The static pressure value should be increasing as you descend.
yeah,
Therefore, you'll start to get an inaccurate reading because the ram pressure hasn't deducted the increasing static pressure. Therefore, your dynamic will be incorrect. Will it be reading too high?
absolutely. So
High.
you're dead correct. So let's have a think about it. Is it going to read, if we're descending, is it going to read in the exam answers? There's obviously going to be one of them that says it's going to read too high and another one that says it's going to read too low. So you've got to work out now which one it is. Now, the way to work it out is to think about it logically. Now, if you're descending, is the difference between the static pressure and the dynamic pressure, are they going to start coming together? In other words, or are they going to start moving further apart? Well, think about it. If you're descending, then the static pressure that should have been cancelling out isn't. So that means that not only so that means that the pressure that's in the back of the instrument is going to increase, isn't it? So that means the two values are going to get closer together. So that means if you start descending, what's going to happen to your airspeed? Is it going to go up or is it going to go down?
They're getting closer together. Will it go down?
It is. The airspeed is going to reduce. So in other words, what's happening is that your airspeed indicator is functioning as a poor man's altimeter, isn't it? So as you start to descend, your airspeed is going to descend. And as you go up, your airspeed is going to go up. So it will still slow down and get more as you increase your airspeed. If you can go faster, it will still go faster. If you go slower, it will still go faster. But of course, it will only show you your airspeed at the previous, the correct airspeed at the previous altitude when the static port got blocked. So that's an interesting one to think about. Now there's normal questions on these things in the exam, but they'll give you probably more than one instrument. So I want to just briefly talk about the altimeter and the vertical speed indicator, and then we'll call it a day. So let's talk about how the altimeter works. So it's very similar in that we've got same scenario in that we've got a tube that's connected to a capsule, a very thin metal capsule. Sorry. we've got a right. So we've got we've got a tube, but this is connected just purely to the static port. So this is just reading the static pressure. And what happens is that this capsule can expand and contract inside the instrument. And as it expands and contracts inside the instrument, it's connected to, once again, it has a, typically it has a tiny wee little arm on it that's connected. Typically, it's connected to a small cog that's like an arc. And then this in turn drives a little cog. Then connected to that little cog, there's a big cog. Connected to that big cog is another little cog. Then connected to that little cog is another big cog. And so it goes on. So that one's connected to another little cog, and that's bolted onto another big cog. And then you've got a series of needles, and you've got like you've got a needle here, and then a smaller needle here, and then you've got like another needle on another cog. So what's happening is that tiny changes here move this, which move that, which move that, and move these things, move all these needles. So typically you'd have, this might be representing sort of feet, and this might be representing, this might be a smaller needle representing like thousands of feet. So this would like be slightly different shape. This might be thousands of feet here. And this might be feet here on this needle. So this needle would rotate a lot more times than this needle. So for every revolution of this needle, this would then probably go up 1/10 of a revolution. Yeah. So it's like a sort of hours and minutes on the clock. They're geared. And so all this is really doing is just showing you the pressure. But of course it's calibrated to convert that pressure into an altitude. And a precision altimeter actually has this subscale on it where you can adjust an extra knob on the front of it, and it's got a subscaler showing you a pressure, and then in this subscale, in your altimeter, you'll see that you can probably set in a window, you'll find that you can probably set something like, it will have a line here, and you can sort of select 1012, or one, and there'll be 1013, there'll be 1011, and you can move a value underneath this subscale, and this alters the base reference, if you like, of your altimeter. So if you're if the C pressure here isn't 1013, if it's like 1012, you can put 1012 on this subscale, and then this will actually be reading you feet above sea level for the day. Yeah, well, not for the day, for the hour. And obviously, as you fly around a bit more and cover more distance, or as the day progresses, this pressure at sea level might change from 1013 or 1012. It might become 1010, in which case you would then move this knob until 1010 came there, and then this needle would move to show you how far above you are relative to 1010. So if you like, what the altimeter is doing is reading you how high you are above what you've set here. In other words, this is your base reference pressure that you set with this, and then this needle moves to show you how high you are above that base point.